This is the screencast for section 2.2, example 5, modeling with power functions. Modeling planetary data with a power function. So in other words, this is not going to be linear, this is not going to be a parabola, it is going to be a power function, y equals kx to the a power. Use the data table in 2.10 to obtain a power function model for orbital period as a function of average distance from the sun. So that gives us a clue as to what our input will be and what our output will be. So we're going to model for the orbital period as a function of the average distance from the sun. So as a function of average distance from the sun means that is our input. We're gonna come out with the orbital period as a function of, depending on the average distance from the sun. So I'm going to put the average distance from the sun as my x values in L1, and then the period of orbit in L2. Go ahead and enter those into your calculator. Now I'm going to, on my calculator, hit Stat, arrow to the right to Calc, and I would like to come up with a you guessed it, power regression. My x values are in L1, my y values are in L2. We don't have to worry about frequency list. We want to store the regression equation into y1, which I have already cleared out. And now I'm going to calculate. So there's my regression equation. As you can see, my R value is extremely strong. This will be very close to my data points. So I'm going to go to second stat plot, turn that plot on, zoom 9, and I can see my points that I've plotted as well as the power regression that I just came up with. And then it says use the model to predict the orbital period for Neptune, which is 4,497 GM from the sun on average. So that means, let's see, I am going to need to make my window a lot bigger in order to see that. So I'm going to go to Window. Since the orbital distance from the sun is an x value, I'm going to have to change my x max to bigger than this 4497. So I'm going to change that to 5,000. So let's change our y max to 100,000. Let's just go crazy and see what happens. Oops, that was 1,000,000. Maybe that would have been good. I don't know. That's better. Now I can see the graph as it traces all the way out to the edge of the window, so now I can see the y values for all of the x values I want to. Now I'm going to hit Trace, and I specifically want to enter the input 4497. Nope, that's not what I wanted to do. I wanted to go to Graph, Trace, arrow to y1, and then go 4497. So what my calculator comes out with is that the orbital period will be 60,150 point, it looks like 07 days. Now I could have taken my power function and plugged 4497 into the equation and calculated that all out with my calculator, but since it was already plugged into y1 and all my stats and my lists, I figured I'll just let the calculator do the work for me. The now try problem for example 5 is number 55, keeping warm. For mammals and other warm-blooded animals to stay warm requires quite a bit of energy. Temperature loss is related to surface area, which is related to body weight, and temperature gain is related to circulation, which is related to pulse rate. In the final analysis, scientists have concluded that the pulse rate R of mammals is a power function of their body weight, W. So here's their body weight, and here's their pulse rate. The pulse rate is a function of their body weight. So in other words, we're looking at R of W. Part A asks us to draw a scatter plot of the data in table 2.12. So our x values, our input values, are going to go into L1. Those are the body weight, because that is what this is a function of. Then the pulse rate is going to go in L2 as our y values, or output values. So of course, I've already done that in my calculator. Go ahead and put those in if you have not. Now the question asks us to draw a scatter plot. So I'm going to hit zoom 9. And you can see that we have a power function, but it's going down to the right. This function is decreasing, which means I'm going to have a negative exponent. I can predict that. So here's my scatter plot. Next, find the power regression model. So stat, calc, power regression. I want my x values from L1 and my y values from L2. I'm going to store this into y1. And now calculate. So there's the regression model, which if I wanted to write that out would be y equals A is 231.20, x to the, and then b, as I predicted, is a negative exponent, 0.297, we'll say. So that's approximately what the power regression model is. Part C asks us to superimpose the regression curve on the scatter plot. So now that I've got this formula that is going to, it's going to model the data points, I can graph one on top of the other and see that that is a pretty close match. Plus, I saw that it would be a pretty close match from the R value when I got the regression model. Part D asks us to use this model that we got to predict the pulse for the rate of a 450 kilogram horse. So let's do that first. 450 kilograms. So we need to change our x values all the way out to 450. So I'm going to go up to 500. So I'm going to change my window, my x max, because the body weight are the x values, to 500. It's going to get very much close to the x-axis here. But now I can hit trace and put in as my x value 450, go to y1, and then hit 450. So the pulse rate for a 450 kilogram horse is going to be 37 point, looks like 70 beats per minute. The second part of this question asks, is the result close to the 38 beats per minute reported by A.J. Clark in 1927? Yes, that is close.